Thank you, Dayan, for the introduction. Thank you for connecting today or coming back. So this is the second lecture of week 4 of Atom, and we are talking about an introduction to Berkovich geometry. So let me start by recap what we did in the first lecture on Monday. So in the first lecture, we work with valuations or semi-norms. So we fix a field K, and we work with, in particular, with non-Archimedean fields. So we endow K with a norm whose distinctive feature is this property in red. So that the value of on A plus B is smaller or equal than the maximum between the value of A and the value of B. And we see how, how this property, all the like strange phenomenon and consequence that having this property can have, and the effect in particular has on the topology, on the matrix topology that we can put on K. So just to refresh, if you want an example, here today we will mainly work with Laurent series in one variable, and the algebraic closure that is called the field of Puiseux series. And also to have a fresh sheet in mind, since we will also work with tropicalization, and there we usually use the additive notation, so we use the valuations. Let me recall you that given a non-Archimedean norm, we can always associate a valuation. The operation that to pass from one to the other is really elementary. We just set V of an element to be minus the logarithm of the norm evaluated at that element. And by convention, since we know that the norm of 0 is 0, then we set minus log of 0 to be equal to infinity. So that's the reason why the valuation now takes value not just in R, but also in R union infinity. So this R bar. And again, the strong inequality becomes, in terms of valuation, the fact that valuation of A plus B is at least the minimum between V of A and V of B. Okay, so the main topic of my first lecture was the introduction of what is a Berkovich space. So we say that basically we have this, if we just consider the K points, we have a pretty bad topological space. It's usually, it's totally disconnected. And so we work with Berkovich space. In some sense, we have new points, and these new points are multiplicative semi-norm that extend the norm that was given on K. So here is the picture of the Berkovich affine line that we constructed together. Maybe if you looked at the problem session, you have seen all the details to construct and prove the kind of points that you can have in the Berkovich affine line. And let me also recall you two important facts that we will use today. So the first one is that we've seen that the K point, also like the point in algebraic closure, if K is not closed, embeds inside the Berkovich space. So this means that all the K points have an associated multiplicative semi-norm that is quite natural. We just take, for instance, a polynomial and we evaluate at the point. Now we have an element in K, so we can take evaluation. And in particular, this subset is a dense subset inside the Berkovich space. So this already suggests an idea that the topology that we are working with, it's quite different than just the usual metric topology of an infinite tree as the one we see here. Because we need to imagine that this point lives at the ends of the leaves. They are the leaves of these infinite branches, but they're still a dense subset in the topology. And then a second fact that I mentioned towards the end is that the Berkovich space has the homotopy type of a polyhedron. And today we will, towards the end of the lecture, try to see how we can, in some cases, construct explicitly this polyhedron. But now, let's start with the first goal of today, that is trying to, okay, so here we have a question. Can we explain why the K points are dense? So if you study the open in the Berkovich topology, you've seen that usually, like for every point that you take, let's take a branching point, an open contains all but finitely many of the branches. So this is, you should use this to prove the density of the xk points. So this is an hint, and then, I mean, we can discuss, I mean, all the details and the complete proof, yeah, maybe in the problem session or also in Piazza. But that's like, yeah, the one argument that you can use. So one of the main goals of today is try to see some instances of the relation between Berkovich spaces and tropicalization. So let me start by recalling you what do we mean here in this school by tropicalization. So I think you've already heard in the talk by Diane, so this was the first week of Atom, that you can think of tropicalization as a combinatorial shadow of algebraic geometry. So basically, suppose that we fix K to be C double bracket, curly bracket T, so this is algebraically closed. We fix F, a polynomial in an variable, then associated to F, we can construct a tropical variety. So here is denoted V or trop F. So we think of F as a, so we associate it to F a tropical polynomial, and then we can consider what are the points in this R and bar where the tropical polynomial has value infinity or attain the minimum at least twice. So here is an example. So if we fix F to be y1 minus y2 minus 2t, this is the tropical polynomial that you get, and this is the picture of your tropical curve. Okay, but then I think that it was probably the subject of the first lecture is that we have a fundamental theorem of tropical algebraic geometry. So we have a second point of view that we can consider if we want to think of these tropical varieties. And it's basically we can take x1 and xn solution to our polynomial in K, and then we can apply the evaluation. So what we will get is again a polyhedral object that coincides with B of trop. So here it's again, I mean, I wrote the detail for this example, but I think that probably you have already in mind these kind of pictures. So what we want to do today is to add a third point of view. So here are the two that you are probably already familiar. Now let's see what is the third one that we can consider. So if you see, when we define trop of x, we choose, I mean, we consider a solution, x1 and xn, and then we apply the evaluation. But now when we work with a Berkovich space, we don't have just the evaluation on the field K. We also have many extensions of this evaluation. So it is quite natural to define a map called a tropicalization map. So we start by defining it on the analytification of A and K. So on the affine space, we have the coordinates y1 and yn. And so this map, what it's doing is taking any evaluation, b of x. If you prefer thinking in terms of semi-norms, I wrote again what does it mean in terms of semi-norm. But let's take evaluation, and then you can just apply the evaluation to the coordinate y1 and yn. So let's see in particular that inside the identification of the affine space, then we will have the identification of x, that is the subvariety we're looking at. And in particular, moreover, inside, we know that we have an embedding of this xk point. So let's see what is the tropicalization map doing on these points. So if we take a point here, it means we're taking x1 and xn. Then if you follow the definition of the tropicalization map, we need to do v of x on the coordinate yi. But now we remember what is the evaluation that is associated to a k point. It's just we take the polynomial, in this case is y1, and we evaluate the polynomial. So what we get is v of the evaluation that is just xi. Okay. But now if you look closely, what you see here is that on the right, with this tropicalization map, we are computing v of xi on the solution x1, xn. But also when we consider trop of x, we are considering vx1, vxn. So it means that what we are taking here via the image of the tropicalization map on the k point, when we take its closure, it coincides with the tropicalization because, if you see, they're defined precisely in the same way. And now, I mean, by using the property of the tropicalization map, the fact that it's continuous and closed, and the fact that these xk points are dense, you can prove indeed that the whole image of the Berkovich space via the tropicalization map will give us trop of x. So here it's written, what we get by like an argument of density is that this image of the tropicalization map, it's really like the tropical variety that we already studied associated to x, okay? But let me make one remark. So I don't know if you have already observed in the exercises or in the previous lecture that everything is written here. It really depends on the embedding. So let's see it like here we fix x embedded via, it's called embedding I inside a finite space. And all these map, I mean, we really use we choose coordinate y1 and yn where we were evaluating our semi-norm, a norm of evaluation v of x. So in some sense, we can imagine that by changing the embedding, we'll also change these maps and their image. So this is, I mean, the game we want to play today now. So we want to see what happens when we change the embedding, and we want to study the tropicalization map under different embeddings. And I decided to just take an example where I think the picture and the ideas are really clear. And I think you will get the main ideas from I mean, seeing the details of the example. So this is an example that I learned from Tyler Foster, as in an example when we will consider different embedding on the affine line. So this is particularly nice because now we should all be quite familiar with the Berkovich affine line. So we know in this tropicalization map, at least we should know quite well the source of the map, like this XAN. And when you consider the affine line, I mean, the first affine embedding that we can consider is just the identity, right? So we can send y to y. And now the tropicalization map, I mean, by definition is we evaluate all the possible evaluation v of x on the coordinate of the embedding. So the coordinate of the embedding is y. So we're taking vx of y. So now let's see, I think, so first let's compute the tropicalization. I mean, this is really easy. It will be just all the elements in R bar. And on the other side, I picture XAN. So now what we want to try to do is pick an element in XAN and see where it's mapped by the tropicalization map. Okay. So let's start with one element. So let's start with eta 0n. So we want to understand where is this sent. So let's follow the definition. And so if we follow the definition, we want to compute y of zeta of 0r. By definition, this is the supremum on the ball of centered 0 and radius r of all the, I mean, we need to take all these elements z and evaluate at this polynomial. So we will get sup of the norm of z. But then this is, I mean, quite immediate to compute. This is just r. So it means here that now we need to take minus log of this value. So we see the tropicalization map is send this eta 0r to the values minus log of r. So let's picture. So what does it mean? It means that this element here at 0, so where r is 0, is sent to minus log of 0. So it's sent here at plus infinity. And then while we're moving towards the infinite direction in the affine line, so r is increasing, so minus log of r is decreasing. So we're moving here along the tropicalization. So already here we found a path in the Berkovich affine line that is sent one-to-one to the tropicalization. But now, what about other points? So for instance, let's pick a point that is not along this path. So let's take like eta AR, and in order to be not on the path, on the green path, we need to assume that the R is strictly smaller than A, because we've seen that as soon as R is equal than A, evaluation of A, then we are here. And then the bolts of radius A and of center A or center 0 with radius R strictly bigger than A, then they just coincide. So we're back to on this green line. So we want to compute here now what's the value. So again, what we need to compute is taking Y and compute its value with respect to the norm eta AR. So now this is a question just to, revise what we did last time. What will be the value in this case of the norm of Y? So if you have an idea, feel free to write your answer in the chat, and I hope I will be able to see your answers. So you can imagine that we are again working with non-Archimedean norms. So we can, the norm of Z, we can again study by, okay. Okay, I can see now a couple of questions that are appearing. I'll just wait a couple of seconds to see if more people are trying to do the computation. Yes. Okay, so all the answers that I can see are correct. So indeed, we get the absolute value of A, because we can think of the absolute value of Z as the absolute value of Z minus A plus A. Then we use the strong triangle inequality. And now since we fix R to be strictly smaller than A, the maximum is norm of A. So it means that now we need to take minus log. So here we get minus log of norm of A. So what we're seeing here is that it doesn't depend which R we take. So for all the R, sorry, let me use another color. For all the R that are strictly smaller than the norm of A, all these valuations, all these semi-norms are all sent to minus log of A. So they're all sent to a point here corresponding to minus log of norm of A. Okay, so what you can prove, and this is also be part of the problem session, is that only the path, the green path, is sent one-to-one to the tropicalization. All other branches that starts from the green path, they will all be sent to just one point in the tropicalization. So the map will not be one-to-one. Okay, so this was when we consider like the really trivial embedding of A1 in A1. Let's try to consider another embedding and see how this picture will change. So now let's consider the embedding in A2. So now we can fix, the coordinate will be Y plus T and Y minus T. The tropicalization map will then be V of X evaluated at these two coordinates given by the embedding, Y plus T and Y minus T. And so what's the picture that we get for the tropicalization? Let's start from that. So if you look closely, the embedding that we define here coincides with the subvariety given by Y1 minus Y2 minus 2T. That's the subvariety we started when I recalled the tropicalization. So we already computed that this will be the picture of the tropicalization. And now we want to see, okay, let me read the question. No, you will get all the real numbers, not just the negative real numbers, because we're getting minus log of R. So R goes from, R is strictly positive, but then when you take minus log, you will get all the real points, yeah. So here, we want to understand now what is going on, okay? What is this tropicalization map with respect to J now doing on our Berkovich space? So if you look at the coordinates, we have y minus t and y plus t. So these 2 points, minus t and t, would be particularly interesting in computing the tropicalization. So these 2 points, they join the path from 0 towards infinity at the point here. They coincide with eta 0 and then the norm of t. So E minus 1, because norm of t is equal norm of minus t, and this is e minus 1. And so what you can prove is that the path joining minus t to these points will be sent one-to-one to this part of the tropicalization, while the path from t to this point will be sent to this part of the tropicalization one-to-one. And then now let's use again grid. So the path from eta 0 e minus 1 towards infinity will be sent to this array of our tropicalization. And again, now if you take some red, yellow path, so paths that are not the one that I just described, you will see that these are not sent one-to-one. So they're just sent to one point. So they all collapse to one point. Okay. So let me make a third example, and then we try to understand what are we visualizing here. So the third example is when we consider now an embedding in A3. So the tropicalization in this case, lives inside R bar 3, and you can make the computation and see that this is the picture that you get. So there will be one part in Y1 and Y2, and then we will get also these two rates in the other direction, in the direction. Let me read the question. Do they all map to one point or to the point where the branch off? No, so each branch is attached to this, for instance, to the green, is attached to the green system. Let's take the yellow one on top. It will be sent to the R corresponding to the branching point. Okay. Okay. So let's move to the example of A3. So here again, we will see that again, the points that we're interested in looking will be the branches, that have as leaves minus t, and now also t minus 1. So the points where these join our main branch here will be, again, this point is eta 0 e minus 1. And while t minus 1 is norm 1, so we'll also have eta 0, 1. And here, again, the picture will be as follows. So we'll have this path that will be sent again to this part of the tropicalization. Then we will have the branch, the path that connect to T, it will be sent to this part of the tropicalization. Then the path from eta 0 e minus 1 to infinity, it will send one-to-one to this part of the tropicalization. And now we have one extra part to consider is the path from here. So from eta 0, 1 to t minus 1, and this will correspond to this part of the tropicalization. Okay, and now once again, what if we take other branches that are not the one that I just described? Then we have again that, the branches will attach to one of these paths, and the points will just be, all the branch will go to the corresponding point on the tropicalization. Okay, so let me sum up the three pictures that we just considered. So here are our three pictures. So in the first, second, and third example. So we see that while we are changing the embeddings, there is a different subset inside the Berkovich space such that the tropicalization restricted to that subset is one-to-one to the image. And we can even say more, like, for instance, the second and the third embedding are such that they have a commutative diagram. So look here on the left. We can just compose by the projection to the first two factors and see that, basically H composed with this projection will give us back the second case J. Let me read the why. In the tropicalization, why? So I'm not sure that I understand. So in the tropicalization, you can have some finite parts, right? I mean, imagine sometimes you have even like loops or things. I mean, not all the rays are unbounded. So, and so what, and also I mean, if what I'm saying, so for instance, if you want to discuss about this bounded part between, let me point it to you, between these points and these points, indeed, it's exactly this bounded part in the Berkovich space that is sent there. So I hope this helps with your questions, and if not, yeah, you can write and ask me again. I will try to, yeah, understand it. Yeah, you answer better if that was not enough. Okay, so here we see that if we consider the second and the third embedding, they are related via projection. And this is reflected also the level of tropicalization. So I mean, basically in a functorial way, we also see with the tropicalization with respect to H, we can just again project to the first two coordinates that here were like omega 1 and omega 2, and here it was omega 3, and we get a map between the tropicalization. So this is, I mean, all the discussion that we have done in just one example. The tropical line. Okay, the tropical line has 3 unbounded rays in this second example, but the paths are bounded. Okay, are you talking about which in second example? So let me go back to the second.
I wonder if the question is that it looks in your picture like the rays are finite length going to the K rational points. So the fact that those have infinite length, I think might not, maybe that's the question. Maybe that wasn't clear to the person asking.
Okay, no, I mean, that's just, I'm simplifying the picture. Yeah, sorry. Yeah, okay. Okay, let me go back to here. So here we say, okay, we observed in this example that we can have different embeddings. Sometimes embeddings can be related by maps like this projection, and these also induce a map between the tropicalization with respect to the different embeddings. So what this is suggesting is that we don't only have a map when we fix an embedding, a map from the Berkovich space to the tropicalization, but constructing on this morphism, using this morphism that relates our tropicalization, we can indeed construct a limit. So we can take the limit of this tropicalization map and see that the Berkovich space will then be sent to the limit of all this tropicalization. And what is, I mean, the interesting part of this result is that this is an homeomorphism. So what we see here, what we are seeing here is that the Berkovich space on this side is homeomorphic to the limit of all tropicalization. So you can take this as a slogan. Berkovich identification is the limit of all tropicalizations. When we change the embedding, of course. So this is a result. I mean, I show you via picture. One example was when we were considering affine embeddings. But this can be, I mean, the result is more general. It's proved by Champagne. You also consider embeddings in toric varieties, but for that it needs an extension of the notion of tropicalization. It's called extended tropicalization. And I suggest you to look at this paper if you're interested in this result. And I also mentioned that the case for the affine, when X has affine embeddings, will also be treated in the problem session. So you will see that, I mean, right now you should have all the tools to be able to prove such a result. Okay, so I mean, this is now, let's pause for a second. What we've seen here, so last time I explained to you what is, I mean, why we need a Berkovich space and basically, I mean, the basic definitions. And now here we see one way to look and maybe study the Berkovich space. We can like study the tropicalizations and get information about the Berkovich space, or also the other way around. I think, okay, I don't know exactly what you mean by intrinsic tropicalization, so maybe I'm not like the right person to answer these questions. But yeah, in a sense, I mean, you need to think that here it doesn't matter. I mean, in the Berkovich space, when you look at the Berkovich space, you're seeing all the embeddings. So sometimes you have problems in tropical geometry in the sense that if you choose the wrong embedding, you might miss some of the topological or geometric feature of your variety. In some sense, this is, I mean, it will correct this problem in the sense that we are taking all. So we should then see all the geometric properties. But I mean, I think this is everything I can say. Then maybe we can discuss about what means intrinsic tropicalization for you in the context here. Okay, so now let's try to move to the second part of the lecture, where I would like to give you another point of view on Berkovich spaces. This will connect more with what you've seen in the talks by Matt Baker, where you talk about model of curves. So he mentioned that there was a relation with Berkovich geometry, and here I will try to give some ideas. So for this reason, we move to models of curves, okay? So for simplicity, let's fix K to be C double bracket T. And we fix a curve over K. So if you want to keep an example in mind now, you can just pick the vanishing of this polynomial, xy minus t in A2, okay? A2 over K. And if you want to think more geometrically, you need to think of this as a family of curves that are parameterized by a parameter. This parameter is t, and t is different from 0 because we're working in C double bracket t, and in this field, t is invertible, so it's different from 0. Then what does it mean to consider a model for our curve x? So it means that taking a model means that now we work over C double square bracket t. So now t can attain the value 0. So it means that our family that was defined over t different from 0, now we want to extend it also over t equals 0. And when we do this extension, I mean, in general, we can extend it, and we can extend it saying that the new fiber that we're adding is not too bad, I mean, not too singular, we will see in which sense, but in general, they could have some singularity. For instance, here, you see that this model is like a node here. So it's no longer a smooth curve. So let me give you 2 or 3 examples of a model so that also you have, I mean, more intuition on what kind of object we are working with. So the first model that you can consider is, for instance, you take the affine line, you can define the affine line both over R and over K, and then the affine line over R will be automatically a model of the affine line over K. And the same for the projective space. So these are the first example you can keep in mind. Now let's see one like not as trivial as the one I just gave. So suppose that you fix a polynomial, this polynomial f, so xy that multiply x plus y minus 1 plus t x cubed plus y cubed plus 1. So you see here that the coefficient depends on t, so depends on this parameter. But if you take the vanishing of this polynomial in A to R, this is a model for the variety defined by the same polynomial, but in A to K. And in particular, what happens when t goes to 0? So when we are, I mean, let's see what is the fiber that we're adding now in this degeneration. I mean, we're saying that taking a model means adding one fiber. So this degenerates to, okay, if we put here t equals 0, then we're just left with this polynomial, and we see that it degenerates to the vanishing of x, y times x plus y minus 1. So these are 3 polynomials. And so it means that we are having 3 components. But let's see, let me say it more. So in particular, we will work with models that are regular in the sense that we don't want to have too many singularities, too many bad points, even if our special fiber, the one over t equals 0, can have some singularities. So as I say, we can have nodes, but this is the worst thing that we can have. So here there is a question, does a model have dimension 2? So dimension depends I mean, you need to fix a base field or a base scheme to talk about dimension. So this is, if you think of this over C, then this is dimension 2. So you can really picture this as a surface over C. But then if you think over K, so your base field is C double bracket T, then this is just like one curve over C double bracket T. So it really depends on, I mean, which base field you're referring to when you talk about dimension. Okay, but yeah, I mean, if you're more like geometric, yeah, let's see this as, I mean, let's see this family as forming together a surface. Okay. And now, so here I say that we want to impose this semi-stability. Semi-stability means that these components are smooth and they intersect transversally. So that's, I mean, the picture that I have here, it's the local model of something that is semi-stable. So you can really take it as, I mean, the main example. And why we're interested in particular in semi-stable is because if our special fiber is semi-stable, we can associate a dual complex. So I think you probably see both Renzo and Matt mention the dual graph or complex. I mean, dual complex if we're working with models in higher dimension, not just with models of curves. And this is an object that is constructed as follows. To each component, we associate a vertex. So here we have 2 green components. We get 2 green vertices. And whenever we have a node, for instance, here we have a node, we consider an edge joining. So the node corresponds to an intersection of the 2 components. So we will connect the 2 components with the edge. Okay, let me make you some example of dual graphs so that we will be sure that everybody's understanding. So let's take the easy model that I say. So let's take A1R as model of A1K. Then if you think of the special fiber, so we put T equals 0, we just have the fine line over C. Now, we have a new question for the audience. What will be the dual complex associated to this model? So I will give you some options. So here are the 3 options. What do you think the dual graph will be for this model? So I will pause a second and waiting for the answer, even if it seems that you all agree from now. Okay. So I hope I can see all the answers. But anyway, yeah, the one that I can see they are correct, we get, so the correct picture of the dual graph is the second one, because the affine line A1 is just one component. So we get one vertex, and then we have no nodes, no other components. So that's everything we can see in the dual graph. Now let's make a more complicated example. So let's pick the model, the example that I mentioned before. So let's take this F given by this polynomial. Let's think of this as a model, and then let's take the special fiber. So here the special fiber is 3 components. I will picture the 3 components here for you. And now again, we want to compute the dual graph. So I will give you again options. And so these are 4 options. Okay, I can see that people are answering the chat. I will wait just a couple of seconds if someone wants to answer. Okay, so it seems that everybody agree that we get the right picture is the number 3, because indeed what we have is that we have these 3 green components, and then we have 3 nodes, and the nodes are always between 2 of them. So we get these 3 edges joining the vertices. So this is the picture of the dual graph. So let's see, let's see what are we doing. So we started with a curve. We say that we can construct models, even nice models, these regular semi-stable models. These are such that the special fiber is semi-stable, and we can associate a dual graph to the special fiber. Okay, but why are we interested in doing this geometric construction? I mean, we say that we wanted to have another point of view on the Berkovic space, right? So the reason why we're looking at this is because of the following proposition. They say that if you fix any semi-stable model, as the one we are working with, then we have an embedding of the dual graph inside the Berkovich space. So let me try to give you an idea of, in which sense we can embed this nice combinatorial object that we just constructed inside the Berkovich space. So let's go back to our main example, xy minus t. Then we see that the special fiber has these two components that meet transversally, and here we have the dual graph. Now we want to see the embedding. So what we want to do is, for instance, let me do it for one of the components. So the vertical component is given by x equals 0. So this correspond to the component x equals 0. And what does it mean that now I want to embed the dual graph inside the Berkovich space? It means that I want to give a valuative interpretation to these points. Now these points are not just parameterized by an interval from 0 to 1. I really want to associate a valuation. So the valuation that we will associate here, for instance, let me call it Vx, because it's associated to x equals 0. Then it goes from, as usual for the point in the Berkovich space, from A to R, and is defined as follows. So any polynomial f in this field, in this ring A, it can be written as a certain power of x times g, where g is not, cannot be divided by x. And then what we're taking as valuation is just the element A. So it means that we're taking the order of vanishing of f along x. Okay? And we can do the same. So, here the component will be VW. So here we will get an order of vanishing along y. And then, how can you think about the point that are here in the middle? Okay? Sorry, maybe this is just y equals 0. It's not yet a valuation. This is just y equals 0. So how do we think of a point in the middle? So this is parameterized by, as I said, alpha in 0, 1. Then you need to think of a valuation that is an interpolation of these two. Okay? So for instance, on x, it will take value alpha, and on y, it will take value 1 minus alpha. And then, we can even, in this example that we have really like explicit equation, we can even see what kind of subset in the Berkovich space we are getting. So here we are really, we have these 2 points, these eta 0, 1 and eta 0 e minus 1, and these correspond to this Vy and Vx. And the edge in between, it corresponds to the path that connect these 2 points. So the reason why I introduce the models is because they come from the geometry of our curve, and they will give us, via the dual complex, some nice subset inside the Berkovich space. Okay, so this is the reason why we are studying this degeneration, because then we can get nice subset. Okay, but we can, again, play the game that we can change the model. So let's see what happens when we change the model. So for instance, now let's call this model, suppose it's called curly x prime. So he has a new special fiber, a new degeneration with more components. Then, since I have new components, for instance, for this yellow one, I need to add a new edge, a new vertex in my dual graph. Also for the red one, I need to add a new edge. And there are also more nodes than before. Now we have also these 2 new nodes, so I have new edges. And what you can, expect to happen is that now we will also get a bigger subset inside the Berkovich space. So for instance, maybe we get these points, and like a point in on another branch, and we will also get the path joining them. So you can imagine that now, if we were describing before the Berkovich space is the limit of all tropicalization, maybe we can also describe the Berkovich space as the limit of all these skeletons. So to make this statement precise, we need one more proposition that I will recall it here. So when we're given a model, we say that we have an embedding, and this is the part that we have here on the left, but we also have a retraction here. So what I'm saying is that not only I can take this dual complex and embed it inside the Berkovich space, but it's also possible to retract all the Berkovich space back to this skeleton. So when I mean retract, it's really like I have a continuous surjective map. But in fact, it's even stronger. It's not just a continuous surjective map. It's what is called a strong deformation retraction. So I don't know if you remember what this means. It means that we have an homotopy. So we can construct a continuous path that will take any point that is outside the skeleton and move it continuously inside the skeleton. So if you see this picture, it means that I can take all these branches and collapse them in a continuous way to the skeleton that is drawn in the middle. And in particular, a property of the strong deformation retraction is that the two objects, they are one, a collapse of the other. So they have the same homotopy type. Okay, same fundamental group, for instance. And so why are we talking about this retraction? Is because it's via the retraction that we can state and prove a result that say that the Berkovich space, XAN, is also the limit of all the skeletons. And here we have the statement. So here we have a second slogan. So we can think of the Berkovich space at the same time as the limit of all the tropicalization, but also as the limit of all the skeletons. In the tropicalization, what we are changing is the embedding. While here, what we are changing is the model. So the two inputs are quite different because one is more like playing with finite coordinates, way to parameterize your variety, embedded in a fine or toric variety. While here, the tools that we use are, in some sense, more like tools of degeneration, tools from, we also want like tools from what is called like rational geometry. So we want to find many models to describe the topology of our Berkovich space. But depending on what you are studying and what you know about the variety, you can use, both these settings, both this approach. So, okay, we have a question. Maybe it's an unrelated question, but can we use this result to explain the statement that an abstract tropical curve, it's a metric graph? So, when you, for curves, so I don't know the answer. I don't know if you can really, if that's enough, but for sure, when we work with Berkovich curves, and especially, in this setting, you can put a metric on this infinite tree. And it could be that this is the metric that you need to endow your abstract tropical curve with a metric. That it's possible, but again, I'm not 100% sure in the sense that, I don't know, what kind of property, what kind of matrix you are looking for. So, just the answer that I can give you is that there is a way to put matrix on this curve, on these Berkovich curves. So, so to conclude, let me, okay. Can you use the Berkovich identification to build a model? So what you can do is, I'm not sure that you can explicitly construct a model, but in some sense, you can read from the Berkovich identification information about models. So, for instance, you can maybe say that, think of, for instance, let's take the example of the elliptic curves. Then, the Berkovich identification of elliptic curves is really nice because elliptic curves, when they degenerate, they have two ways to degenerate, good or bad reduction. It means that one degenerate to a smooth elliptic curve. So it means that this dual graph is just a point, while the other one can degenerate to a chain of rational curves. So it means that the dual graph will be a sphere, right? And you can see, so it means that in one case, your Berkovich space will be just contractible. In the other case, there will be an S1 inside your Berkovich space. So for instance, this is a property that you can read from the Berkovich space, and it will give you information about the elliptic curve. For instance, it will tell you if it's possible or not to construct a model for your elliptic curve that is smoothed also in the special fiber. So, I mean, these kind of things you can, I mean, there is really nice interplay. I mean, if you really mean building by, I mean, getting and constructing explicitly, then I think it really depends on the case you are studying. Okay, but let me wrap up and conclude. So what we've seen today are these 2 points of view on the Berkovich space, at the same time as the limit of all tropicalization and the limit of all skeletons associated to models. So as I mentioned, it really depends on the context and on the tools that you want to use. You can take one or the other. So for instance, like the skeletons will give you explicitly a polyhedron that sits inside the Berkovich space. If you remember, we mentioned the result by Rujovsky and Lozer, that the homotopy type of the Berkovich space is a polyhedron. Well, here it's a way to construct it explicitly. While also, I mean, the approach with the skeletons works in higher dimension, even if you don't have equation or embeddings. And I mean, one last example I want to conclude my lecture today is an example where we see that, I mean, if we fix one embedding, we will see that the picture of the tropicalization and the picture of the skeletons are quite different. So let me state the example. So we take f to be given by y times 2y minus e squared plus 1 plus t. Then you can embed this in A2K. In A2K, and this will be the tropicalization. I mean, if you consider the tropicalization with respect to the embedding I, this will be the picture of the tropicalization. But then let's see the model associated. So using the same equation f, we can also associate a model. This model will have a special fiber. We just put t equals 0. So here we put t equals 0, and we're just left with the remaining part of our f. And we see that this is given by y equals 0, that is a line, and then a parabola. Then the dual graph associated will have 2 components, but they meet in 2 points. So 2 nodes means that we need to consider not just one edge, but 2 edges, because we have now 2 nodes, 1 and 2. But then we have the result that the Berkovich space is the same homotopy type of the dual graph. So it means that the picture of the Berkovich space will be the following. Will be an S1, and then everything else is just something that can retract back to this dual graph. So here is an example where, I mean, if we pick, it's possible and visible that if we pick the wrong embedding, then just one individual tropicalization may fail to capture the topological property of your Berkovich space. While, for instance, the skeletons will always be homotopy equivalent. So you will see also, I mean, we prepare a couple of examples where you will use both tropicalization and the skeletons and prove, I mean, and study better and try to understand better the geometry and the topology of this Berkovich space. So I think that I will stop here and let the last couple of minutes for questions or doubts or comments or things. Thank you very much.
Thanks a lot, Enrica, and I hope you'll join me in thanking Enrica in the chat. And once we've done the first round of that, maybe any questions. And I think at this point you could also feel free to unmute yourself and ask the question verbally if you would rather. Oops, there's a couple of questions going by, which we will have to.
I hope I will not miss them. Okay. Can you please repeat the embedding of the dual graph of inside the Berkovich? I understand how you embed the points in the interior. Okay. I will go back. Let me just read also the other. Given a choice of a semi-stable model for a curve C, is there a way of directly constructing an embedding for C whose tropicalization is the dual graph of X? So you want to, okay, I will take them in order. So let's go back to the embedding, sure. Okay, so we are here, right? So is it clear how we embed the endpoints? I mean, we have a segment. Let's say that we parameterize it by 0 and 1. Then the two endpoints are this order of vanishing. Okay, I hope that's clear. Otherwise, just write it in the chat and we repeat. Okay, now we want a point in the middle. So a point in the middle is associated to alpha. And now how we can embed it. So you can, I mean, we will impose that V of alpha of X is going to be alpha, and V alpha, so V alpha is the valuation that I'm associating to alpha, okay? Will be V alpha of Y will be 1 minus alpha. So on the first step, this is the condition that we impose. And you see that when alpha is equal to 0, for instance, we get, here we will have that this correspond to V when alpha is equal to 0, because the order of vanishing of Y at Y is 1, and the order of vanishing of Y at X is 0, while this other V of X will be V of alpha equal to 1. So already you see that the condition that I gave give you back the two endpoints that I described. Now, the question is this enough? I mean, is enough to impose V of alpha on X and Y? Well, it's enough if you say that you can construct a minimal valuation, minimal valuation with these properties. So then there is like a unique point that you can construct, and you will see that, basically imposing these two, it's enough if you also add the minimality condition. So I will probably put an exercise in the problem session where you can really like work these details out, but this is the idea and the way you can, this is the reason why I say the points in the middle are interpolation of the order of vanishing. I hope that's clear.
Can I ask a follow-up question to that?
Sorry?
What if there's more than one edge connecting X equals 0 and Y equals 0?
You mean in the Berkovich space or in
the dual skeleton?
Sorry? In the dual graph? Yeah. So you mean that, okay, so what you're asking is what happens if here I have another one, right?
Yes.
Yeah. So, what does it mean that you have another one? It means that basically there are two intersections between these two, right? Like this, these correspond to the other nodes. So then what you will have is that at this node, at these two nodes, you will have different local equation. So here you will have X, Y, but here maybe you will have like, let's say F, G that describe this node. And then you will use, it means that here locally, you will use the order of vanishing with respect to F and the order of vanishing with respect to G. And so it will be like automatically at different points, the one you are constructing. So the thing is that at each node, I take local equation, and X, Y were local equation only at that node. And each node has different local equation because what is vanishing at one node is not vanishing at another node. Is that clear?
Yes, thank you.
Yeah, you're welcome. Then there was another question. Given a choice of a model, I will answer something related. I'm not sure that is exact. Maybe it will also answer your question. In a sense, the thing you're asking. Suppose that I know from the Berkovich point of view that inside the Berkovich space, there is, for instance, this S1, like there is like a loop, a circle or something. Can I construct an embedding of my variety such that tropicalization will see this circle? If this is the question, then I can tell you that, for instance, for elliptic curve, this is true. You can always find an embedding, even in A2, that, such that it will be, when you consider the tropicalization map, the one we discussed in the first half of the lecture, then on the skeleton, so on the skeleton, it will be one-to-one. So it means that the tropicalization will not collapse or kill this important part that is the skeleton of your Berkovich space when you take the image via the tropicalization. Okay? And then, can you say what the transition maps are in the inverse limit of every skeleton? Okay, so here is the question I think that is related to here. Okay, so what's the idea? So suppose that you have different models. First, you need to relate the models. And this is saying, I mean, you consider when a model dominates the other. So basically you consider when, let me write it here, when you have a model curly, and you have curly x, and you have a model curly x prime, you say the one dominates the other when you can write a map between the two, such that when, such that it gives an isomorphism of the variety of the curve x that sits inside the model. Then when you have a domination of models, then you will also have an induced map from one skeleton to the other. And this will be the one that you will use to relate the different skeletons. And then, can you give us some more reference for the result relating the dual graph of and the identification? So, I mean, if you're just interested in the case of curves, then I feel like Baker-Rabinov Payne is one of the best reference that you can have in mind, that I have in mind, sorry. If you're interested in things in higher dimension, like with, not just curves, then I would suggest you to read Mustat and Nikese. So I will write down and also include this in the list of reference. And then, okay, can you give an embedding such that the corresponding tropicalization? Okay, I don't know the answer to Felix's question, so if anyone has an answer, yeah, feel free to interact and write in the chat. And then we have, in the example of the family Vxy minus t, you said that the dual graph maps to the line segment in the Berkovich space joining. I think, why does Vx map to, okay. Okay, so here, first remark, what was the variety that we were studying? When we study Vx minus t, we are studying a torus. So it means that from the identification of, we're not working with A1, we are removing a point from A1. So this also means that we need to remove a point also in the Berkovich space. So now, this was the first remark I want to say. Second remark is that you need to fix coordinates. So you need to fix, so normally like the torus you think is associated to the coordinate ring k, z, z minus 1. So you need to fix an embedding, a map from x, y minus t to k, z, z minus 1. And what you can do is that you can send, so maybe I go back and write. We are here, right? I think, yes. So you can maybe choose, we can work with k, z, z minus 1. On the other side, we're working with k, x, y minus t. Then I think that, first you need to fix a map to see the 2 points that I described here. And I think that you can fix z equal x. And then you will see that then, the inverse of x will be t over y, right? But y, wait, so now it's x, t over y, so y over t. Okay, so first you fix this, and then you can use this coordinate and describe these points in the way I gave. Okay. Another question is, cannot recover the geometry of X from the identification of XK. What about XAN? So I will try to give an interpretation to the questions. You mean, I mean, probably this goes back to the discussion we had on the first lecture. In some sense, just taking the XK point is not enough. I mean, even the topology there is really bad. And we've seen, like, we've even seen some illustration with the example of the theorem of Serre, that basically, I mean, the definition of what is a continuous function is like not the definition that you will desire, and especially since it's not the right definition, you will get too many isomorphisms. So basically, there will be too many non-isomorphic variety that when you just take the K point will be isomorphic. So you're losing information about your variety. Well, the Berkovich space does not do that. So especially, I mean, if you work with a proper variety X, you really have like what are called Gaga type theorem. So studying the proper algebraic variety with its function is the same as studying its identification with its analytic functions. So I don't know if that was the question. I mean, yeah, feel free to ask more.
Well, I was about to say thank you, but there's one more question.
Okay. What is the definition of semi-stable embedding you're using for the description of the Berkovich space as the limit over semi-stable model as it has to be regular and flat? So if you want the technical definition, you want it to be regular, flat. For that result, let me go to the result here. I mean, normally semi-stable, I mean, it depends on the definition that you pick, but it also requires that your components are all irreduced, are all reduced. So they do not appear with multiplicity. But for this result, you can prove it also with multiplicity. So in some sense, it's a relaxed version of like semi-stable, but still you need to have flat and proper, flat and regular, sorry, yeah.